Hey there, young scientists! Welcome to today's Explainer. We're about to go on an absolutely epic adventure together. We're literally going to step into the shoes of a scientist and follow a single beam of sunlight on its spectacular journey from the blazing hot surface of the sun all the way down to Earth. It's going to be awesome, and we're going to unlock exactly how light travels and paints our world. Okay, let's dive right into this. Have you ever looked up on a beautiful, perfectly sunny day and just wondered, why exactly is the sky blue? I mean, it's one of the biggest mysteries we notice when we're little. It might seem like a super simple question, but the answer? Well, it involves some really magical properties of light, the invisible air around us, and a truly fascinating science phenomenon happening right over our heads every single day. So let's solve this mystery together. So here's our quick roadmap for the journey today. Just 3 steps. Step 1, our light leaves the sun. Step 2, it hits Earth's atmosphere. And step 3, it finally reaches your eyes. Sounds pretty simple, right? Well, that middle step is where the real magic happens. All right, starting with step 1, leaving the sun. Now, when sunlight beams down on us, it just looks completely white to our eyes, doesn't it? But actually, that white light is a total master of disguise. It's hiding an incredible secret rainbow inside. If we could somehow magically unpack that single beam of white sunlight, we'd see all these different colors traveling closely together. We're talking red, orange, yellow, green, blue, indigo, and violet. Literally every single color you see when a gorgeous rainbow stretches across the sky is packed right into that everyday beam of white light. They're all taking the trip together. But here's the catch. These colors do not all travel the exact same way. In science, we say different colors of light have different wavelengths. Now, to make this super easy to picture, let's just think about them as footsteps. Red light has a long wavelength, so just imagine it taking these really long, lazy, giant strides as it walks. Blue light, on the flip side, has a very short wavelength. Imagine it taking tiny, super fast little steps. So, the absolutely crucial point is what happens when these colorful, stepping light waves finally hit Earth. Suddenly, their smooth, easy trip through space turns into this massive, invisible obstacle course. You see, our air isn't empty. It's packed with billions and billions of tiny molecules, mostly making up gases called oxygen and nitrogen. Now let's picture how our light waves handle this giant obstacle course. These tiny oxygen and nitrogen molecules floating in the air are actually a lot smaller than the light waves themselves. Because the red light is taking those big, lazy, giant strides we talked about, it literally just steps right over the tiny atmospheric obstacles. It doesn't even notice them. But the blue light? Remember, it's taking those tiny, fast steps, so it trips, it hits those tiny molecules and just bounces everywhere. We actually have a super cool grown-up science word for this whole tripping and bouncing process: Rayleigh scattering. All that really means is that the tiny molecules in our air scatter the shorter wavelengths, like our tiny stepping blue light, way, way more effectively than they scatter the longer wavelengths. And because of this Rayleigh scattering, that blue light is just bouncing around like absolutely crazy in the atmosphere. It gets scattered in literally every single direction as the sunlight tries to push through the air. So when you look up, all this bouncing scattered blue light finally reaches your eyes from all parts of the sky above you. It's almost like the sky itself is painted with all the blue light that tripped over the air molecules. But wait just a minute. If you're a really clever scientist, you might be thinking right now, hey, if violet light has an even shorter wavelength than blue light, meaning it takes the absolute tiniest steps of all, shouldn't it trip and bounce the most? I mean, why doesn't violet win the color race? Why isn't the sky violet? Now, what's really interesting about this is that the first reason our sky isn't violet is actually really simple. The sun just emits slightly less violet light than it does blue light. So right from the very start of the journey, there's just less violet light entering our atmospheric obstacle course to get bounced around in the first place. But there's a second reason too, and it's this incredibly cool biological secret hiding right inside your own eyes. Our human eyes are naturally much more sensitive to blue light and way less sensitive to violet light. Because our eyes prefer the blue, that's the color our brain registers, so we perceive the sky as beautifully blue. Let's move on and see how this builds, because we've totally solved the daytime mystery, but what about the evening? The secret to those beautiful, fiery sunsets actually lies in the long journey to the horizon. When the sun gets super low near the horizon, everything about our light's journey changes completely. Just think about the difference between noon and sunset. During the daytime, when the sun is way high overhead, the sunlight has a pretty short journey down to us. It hits the obstacle course, the blue light bounces everywhere, and boom, we get a blue sky. But at sunset, because the sun is way over on the edge of the horizon, its light has to travel through so much more of the atmosphere to reach your eyes. It is a drastically longer obstacle course. And because that sunset journey through the atmosphere is so incredibly long, all of that tiny stepping blue light gets scattered completely out of the direct path. It actually gets bounced away before it even gets close to you. So, what's left? The longer wavelengths. Because the red, orange, and yellow light take those giant, lazy strides, they step right over the obstacles, survive the massive trip, and make it all the way to the finish line to paint our evening sky in beautiful, warm colors. This simple phenomenon really shows how something as small as tiny, completely invisible molecules in the air can create the most beautiful sights on Earth. So the next time you look up at a bright blue sky or a stunning golden sunset, just remember, you're watching a grand science experiment in action, with billions of tiny molecules working their magic. Which leaves us with this final thought. If the air is filled with bouncing blue light right now, what other invisible wonders are happening right in front of you? Keep your eyes open, stay curious, and thank you so much for exploring with me today.